And we're back. Welcome back from the weekend and happy Tuesday. Today, we will pivot and turn our attention to a special kind of data, in particular, image data. In order to motivate image data, we have to look at where images come from and how you represent them. But before we can represent them, we have to know how you capture or form images. Homework number 2 has been released. It will be due on the 16th, a week from today, Tuesday, on February 2021 at 11:59 and 59 seconds. Okay, throughout life, whether we are infants, young adults, or in our elder years, the human visual system is quite important throughout all stages of life. Now, humans are inherently visual. Our brain processes imagery and visuals 60,000 times faster than text, and in fact, 70% of your sensory reception reside in your eyes, and 90% of all the information transmitted to the brain is visual. At any moment in time, half of your brain is active for visual processing. And people just in general, 40%, respond better to visuals. So the ability to see, to process visual information is very, very important to human beings. So let's take a look how this light is captured that enables vision. And this is a cutaway view of the human eye. Light enters in through the lens and goes in through the pupil, and it comes to rest. It strikes the back wall inside the eye organ, and it's coated with cells, rods and cones. And these cones are densely packed towards the middle of your eye, the so-called foveal region, and then it's less densely populated along the periphery. Now, these cones respond to various frequencies of light, which send impulses to your brain, and that's what you perceive as color, as visual things. And so this diagram looks at the angle associated with the cone for field of view associated with the eye. Now, 2% in the center of your field of view is a so-called foveal vision. That's the most clear, most high definition, if you will, vision. And the reason for that is that what you see in the 2%, 2-degree cone in your eye is that light that strikes the densest populated part of your eye, most densely populated with the cones. So you have a lot more receptors in the center, and therefore your vision in the center is the most high definition, most crisp, most descriptive. And then 10 degrees out, that cone is called parafoveal, that's less so. Then you have the 60-degree cone, that's near peripheral. And then you have the 180-degree cone, that's peripheral vision. And so if you were to represent your vision pictorially, visually, if you will, the most clear in color, high-def vision is right there in your foveal. And then parafoveal, it gets a little bit less high quality. And then as you go towards the periphery, it's a lot more blurry and less high def. And you don't even really see color, but you see motion for objects. And so this is a depiction of the various regions in the field of view for a human. And when you take an infant, you can take the infant's neck, and there's a reflex here at birth called the tonic neck reflex. And when you have an infant, you turn their head gently and slowly, and as you turn the head gently and slowly, a hand pops up, and it looks like this. And if you look at this, you'll notice, let me set my pen, you'll notice that the infant's field of view, if we look at the foveal region, extends all the way out to the infant's hand. Now, of course, you might wonder, why is this the case? Well, early in life, infants, they touch a lot of things. And when they're developing early representations for what objects in their world look like, they want things that they can grasp to be the most high definition, high quality description. And that makes sense, because if you're going to grab something, you're going to turn it and you want the highest definition, most high quality visual descriptions. Now, you'll notice this is perfectly aligned. And this tonic neck reflex is a reflex that infants are born with, and it conditions them for learning what things in the world around them look like. And so, as an infant learns visual representations, this helps that he or she has the highest quality information available. And so this looks a lot like Usain Bolt. So if you're wondering, Usain Bolt is doing the tonic neck reflex. All right. So if we look at a cutaway view of the human eye, here we have some object in the world, and rays of light bounce off of this object, and they are collected inside of your eye and come to rest on your retina, where you have the region coated with cones. And so here, when the rays of light enter the eye, they bend to a certain degree, and they cross, and we see as those rays of light come onto the surface of your retina, the back of your eye, the cones, you see an inverted picture of this object. And this really does happen, but your brain inverts this picture, and you see things as right side up. Now, let's take a look at this abstraction, because that's exactly what cameras are. They're abstractions of what happens in nature. And so the pinhole camera was the very first abstraction, and here we have an object in the world, and the rays of light come in through pinhole, they're collected, and they come to rest. These rays of light strike the back of this box. Now, the back of this box, you see an image. Therefore, this is called the image plane. It's a planar surface where you get that image captured from the rays of light that bounce off of that image collected inside of this box passing through the pinhole. And so this is some examples of real pinhole cameras. They're wooden boxes, and you cork it up, and you have a pinhole, literally, in some film or paper. And when you uncork it, the rays of light from objects around it, in front of it, come in through the pinhole and come to rest along the back. And there's a photographic plate that sits in the back, such that when it's exposed to those rays of light, it captures the image. And so this is the back of the pinhole camera. The plate slides into this box, and you make sure you put a blanket or something very heavy, thick, and opaque over yourself so that the light around you doesn't pollute and cause bright spots on this photographic plate. But nonetheless, you get in the dark on the back end of this thing, put in the plate, and then uncork it, and then wait a few seconds, recork it, and then take the plate, cover it up so that it's not exposed to light, and then you bring it back to wherever it is, your studio, that you develop it. So this is an actual pinhole camera. Now, of course, you can buy pinhole cameras on places like Amazon online. They're little pinhole camera kits where you can expose film, and then you just take this to your local drugstore and develop it. And so this is really what cameras were way, way, way back. I remember when I was a kid. All right. Nonetheless, when we make this all digital, we take our object in the world, and those rays of light, as we said, bounce off of that object, and they're collected through a lens. Now, what the lens does, it bends. It's made out of glass, and it's a type of prism, so it's going to bend and alter the path that these rays of light take when they come and strike and go into this glass. And so these rays are concentrated by the lens, and they pass out, and they strike what looks like the back of that pinhole camera, but this is a sensor. It's either a charged coupled device, or CCD, or a complementary metal oxide semiconductor, CMOS. And the sensor gets excited in different places, producing voltage levels when different frequencies of light, these rays, come into contact with it. A digitizer reads these voltages, these energy levels, and converts them to values that you represent on a computer as a digital image. And so each one of these cells represents one of those encoded values, representing one of a number of voltage levels for the excitation of this sensor device in each of those locations based on those frequencies of rays of light that are striking it. And so all of this together is the basic digital camera. And so when we abstract this mathematically, well, we have our optical axis, that's the blue here, the z-axis, and that represents the center of the field of view. If we trace the optical axis all the way back to where the rays of light strike the back of the box, the image plane as it's called, that center that it pierces is the foveal region. And so we have some object in the world, and there's a point off of which light reflects, and it comes back into the camera device, and it strikes the image plane. And where it strikes the image plane is that point that is captured ultimately by the sensor and the digitizer as your image. And so this image plane is where the light strikes the sensor device, and that's captured in the form of a digital image. Now, of course, if these rays of light come all the way into the camera, at some point they will converge to a so-called focal point. That's back here. And so this plane where the focal point exists is called the focal plane. And so we define a coordinate axis, x and y, on the focal plane, and the optical center here goes from the focal plane through the foveal region on the image plane, projected out as the optical axis. And so the focal point is where these rays of light come to the focal point. They come to a point. And so there's this thing called a focal length, and the focal length is the distance between the image plane and the focal plane. Focal plane is that plane where the rays of light come to a focal point. They come to a point. And so if you increase the focal length, what happens? Well, the image plane is closer to the object in the world, and these points, because these points converge to the optical center, what ends up happening is the image on the image plane starts to look bigger and bigger and bigger. Because if you imagine we have a cone of light coming in and converging, and if you move the focal length or increase the focal length, the image plane moves in this direction along the optical axis. And if you do that, it's slicing, if you will, this cone of rays of light further down the cone. So you can imagine if you have rays of light coming down a cone and you were to slice it further towards the focal plane. Here's the focal plane. Here's the image plane. If this image plane sliced this cone of light closer to the focal plane, well, it's going to be on the narrow part of the cone, and the result is that the resulting image is going to be smaller. And so what ends up happening is gathering in rays of light from a wider part of the cone coming in, and that's more of a telephoto, wide area type of view. And so if the image plane is closer to the object, that's like a zoom action, because you're slicing this cone closer to the object, and it's a thicker part of the cone, and the image that you get on the image plane is much larger. And so in the first case, if your focal length is smaller, that's like a wide area shot. And if your focal length is larger, image plane moves forward, that is a telephoto, that's a zoomed in shot. So this example illustrates that. And when you see these numbers here in millimeters, that represents the focal length. And so here we start out top to bottom, left to right with a smaller focal length. So that means the image plane is slicing this cone of light. Here's our focal plane. Here's our image plane. The image plane is closer to the focal plane. That distance between image plane and focal plane is 18 millimeters. And so we get this wide area shot, gathering in a lot of light. Now watch what happens when we increase the focal length to 24. You notice the size. This tree moves off to the right, and this mountain also moves off to the right. When we go to 35, you see how big the tree is. It still is bigger, but we see less and less of the picture. just to the left edge of the tree, well, it almost cuts off, but here we see a lot more of the mountain that's to the left edge of the tree. Now when we go to 55, 85, 105, now this fence starts to come into view. You see that fence, and the house starts to get bigger and bigger and bigger. And then ultimately, as we go to 300 millimeter focal length, that house fills up a substantial part of the image, and we don't see any of the mountain, and we see very prominently those trees that are around the house. And so one of the things that is done in modern cameras is you take these lenses, and these lenses capture more light because it bends the rays of light. And so it fans in those rays of light down to a focal point. And you can put all sorts of lens systems on this idealized model of pinhole camera and bend and shape light to gather a lot larger, wider cone of light so that you can get really zoomed in shots or really zoomed out wide area shots. And so here we see an example of what a lens does, and the rays of light come in. Some are parallel and some come to the focal point, and they come in. There's a front focal point and into the lens. It bends and shapes them down to the focal plane and then to the image plane where we capture those rays of light. And so we have two focal lengths, the front focal length and the back focal length, and that describes these points of crossing where these rays come to focus. And so the rays come in to a front focal point, they cross, come into the lens bends and shapes these rays down to the back focal point. And so you can move this lens forward or backwards and alter the width of the cone of light that this system captures. And so this is a modern single lens reflex camera, and you can see a lot of different stages for lenses. We have this lens here, and we have that sheath. It captures light, and that lens bends down the light. That light is passed through some focusing mirrors, and those mirrors shape that light. So here we have the light coming in. It gets bent by that lens, refracted, further shaped by the other lens down to a focal point where it is split with a special mirror system, and you see through the eyepiece the same image that is going in through the image plane down to a focal point. Okay. And so by changing the length between this front lens and these other stages, whether automatically through zoom, auto zoom, autofocus, or manually by moving it forward or backwards by turning it clockwise or anti-clockwise, you can change the focal length and alter the cone that comes in to the sensor. And so you have your working distance, and you have your angle of the field of view, and the height of the field of view for the objects in the environment, the object plane that you're going to be viewing, from which you're capturing these rays of light. And so we have inside of the lens our front principal plane, and so the lens bends and shapes this cone of light, and it comes to a focal point at the front principal plane. It shapes and bends this light, projects it backwards to the rear principal plane, and then it comes to rest on the image plane where it's imaged. And so by changing this lens, you can bend and shape that lens, that light, that image that you produce, using the distance between the front principal plane and the rear principal plane and the image plane. Okay, so the problem with imaging, one of the issues is you get so-called projective distortion. Here we have a plane, a canvas, and here we have a cube, and what you're seeing is the energy that is reflected off various points on that object in the world. And so you have a three-dimensional world, and you're capturing a two-dimensional slice or depiction of things that are in three dimensions. And so here we've projected in this picture those points for the corners of the cube onto the canvas, and the rays of light from the cube are being imaged by this two-dimensional plane. The inside edge, just by the distortion, is going to be represented as this smaller square, and the outside edge is going to be represented by this larger square. Now, if you look at the image, what you see is the front edge and those lines along here that connect the front corners to the respective corners of that back plane. And so you see this image as a two-dimensional representation of this 3D object. Likewise, if we look at this right triangle on the plane, ABC, when you look at this triangle, you get a distortion. It's no longer a right triangle when these corners and these edges are projected onto this plane. And this is so-called projective distortion. And so if you're going to get this projective distortion, one of the practical issues is how do you recover the ground truth shape? Well, let's pivot to the representation of color. And color is represented by so-called color spaces. Now, I'm not going to cover all the color spaces. I'm just going to cover one that we'll be using in this class, RGB Color Space. Now, RGB Color Space is represented as a position on the so-called RGB color cube. Now, this cube consists of three axes, one called the red axis, the green axis, and the blue axis. And so each position in this coordinate system represents some mixture of red, green, and blue. And so if you choose a different location in this three-dimensional space, that location represents a color. And so this color cube in RGB, the different colors are representing all of the different mixtures you can have of red, green, and blue in order to produce that color. And it just so happens with the color cube that if you go to origin, that means 0 parts red, 0 parts green, 0 parts blue, that's black. And every line across this diagonal that connects origin to the opposite corner, that represents levels or shades of gray. Now, each level or shade of gray is representing an equal mixture of red, green, and blue. And that's so-called grayscale line in the RGB color cube. And so each coordinate represents the mixture of RGB, red, green, blue, resulting in a particular color. And so when you go to an HTML website, one of the things you can set is the background color. And the background color is in hexadecimal, which is base 16. And you can specify the first two hex digits. These are 8 bits, so each hex digit is 4 bits. You can specify the number of, or the level of red, of green, and of blue. So if you specified all zeros, 0, 0, 0, 0, 0, 0, that's no red, no green, no blue, that's just black. And so with this background color, you can create your own mixture and define the color of the background for an HTML file. So let's try this in HTML. We're going to bring up a browser and actually show this in action. So we're in the terminal, and I've created an HTML file. So we're in the terminal, and I've created an HTML file, and in this HTML file, it defines a basic web page. So we have the HTML, we have the body of the web page, we'll print some text, and we're going to set background color to 00, 00, 00, 00. So that means 0 parts red, 0 parts green, 0 parts blue. So let me bring up a browser, and in this browser, I'm opening up this test file, and you can see when I load it. So in a browser, I'm opening this test HTML file, and if I reload it, you can see that it's just black. 0 parts red, 0 parts green, 0 parts blue. So let's try something else. And let's now set to full amount of red. So FF, that's 255 parts red. And so red can be a minimum value of 0 and a maximum value or full saturation at 255. So this is full red, no green, no blue. So I'm going to bring back up Firefox. Let me reload, and you see all of a sudden Firefox has a red background. Now, if I didn't like that amount of red, I could certainly change it. Let me change it from 255. Let me make it F0, and we'll see what result we get. So let me bring back up my browser. Now I'm going to reload, and you see it got a little bit less intense. But let's change this some more. So let's make this 40. Okay, so let's save that. Bring back up the browser. Let's reload, and we see it's a much deeper red. Okay, so let's turn off the red. Bring that back to 0, 0. Let's try the green. So if the green, FF, we'll see when we bring back up the browser, we reload, and we see it's full green. Likewise, we can turn off the green and bring up the blue. So that last 2 hex digits, F are FF. Save that. Bring back up the browser. Let's reload, and it's blue. So now, if we wanted to have a mixture, well, let's try a gray level. So we're going to say F0, F0, and F0 equal parts red, green, and blue. So we'll bring back up the browser. We'll reload it, and that's white. Just a little bit too bright. So let's call that 80, 80, and 80. We'll see another shade of gray. So we'll bring back up our browser, and we'll try that, and here it is, we get gray. So this just shows you that by mixing these red, green, and blue proportions, we're selecting a color, and it's governed or scribed by the RGB color cube. And it's a so-called RGB color space. Okay, so let's go back to PowerPoint. I will meet you in PowerPoint. So we're back in PowerPoint, and we've just shown how mixtures from the RGB color cube gives rise to a certain color. So when we represent an image in a programming language, an image is represented as one of these stacks. We have the image measurements, and in this image, in so-called image coordinates, we have m rows and n columns for some value of m and n. And these are the so-called image coordinates. Image coordinates. And these image coordinates describe where in the image you are, which pixel you're referring to. Now, you'll notice here there's 3 slices for the height. This first slice represents the amount of red. The second slice represents the amount of green. And this third slice represents the amount of blue. Now, each of these pixels corresponds to a value between 0 and 255, describing the amount of red, the amount of green, and the amount of blue. So if we set the color of this pixel maybe to that gray level, we would have 80 in hexadecimal for the amount of red, 80 in hexadecimal for the amount of green, 80 for the amount in hexadecimal for blue, and that will correspond to this pixel here being that color of gray. And so each one of these cells is represented as 8 bits because we need 8 bits to represent a number in that interval between 0 and 255. Okay. And so name-wise, we call that first slice the red color channel, or the red plane. We call this the green color channel or plane, and the blue color channel or blue plane. And so we have each pixel is just a mixture of the red plane, the green plane, and the blue plane. All right, so let's try this out in MATLAB. I will meet you in MATLAB. So the first thing I do when I visualize these pictures, I read in the image, and I set some constants in lines 6, 7, and 8 for the red plane, the green plane, and the blue plane. And then I make some measurements. I want to know how many rows, columns, that's my m by n, and what's the depth, which is 3. So then I create 3 different versions of the image. One that's red only, one that's green only, one that's blue only. So I allocate one of those m by n by 3 representations of my image, and in one of them, I'm only going to fill in the values of the red channel, the red plane. Everything else is left to 0. Likewise, for the green channel, I'm going to fill that in. Everything else is going to be left as 0. And I'll do the same for the blue channel. Just fill in the blue channel for my copy of this m by n by 3 image. So now I set my red image data structure to be all the rows, all the columns, just the red plane. And the red plane is the first one. So it goes through all m by n cells for that first plane, the red color channel. I do the same thing for the green plane and the blue plane. Then I compute a figure, plot it, and show you the histograms. All right, so let's do this. So let me run. Oops. So let me run. And what we'll see is 2 figures. One figure is for the first image. The other figure is for the second image. And so in these images, let me blow them up a little bit. We see a picture of the dog. That's the original photograph. And the 2 pictures. One, the dog is kind of turning around. It's on grass. And the other, the dog is standing, or sitting rather, in the grass. And so here we have the original image. Just to the left of that, the second image from left to right, we have the red version of the image. That's just the red color channel, the green color channel, and the blue. Down below, we have the histograms. The histogram for the red channel, the histogram for the green channel, and the histogram for the blue channel. Now, in this case, it's telling you the distribution of pixel intensities, how many of those red pixels from the red channel have an intensity for certain bin values. And so we see here red, that's right around 100, is the most widely represented. In the green channel, the most widely represented green is about 150 saturation. And for blue, we have relatively small amount of blue. The largest represented blue is around 50 saturation. If we look at this other picture, we see a different distribution of the red pixels, the green pixels, and the blue pixels. And so this is just a demonstration to show you how you might depict the composition of an image. And an image, the original image, is nothing more than a mixture, for example, in this upper right-hand pixel, a mixture of the upper right-hand amount of red, upper right-hand amount of green, upper right-hand amount of blue. Put them together, you get this color in the upper right-hand corner of the original image. Okay, so let's go back to PowerPoint. So this is how an image is represented in programming languages like MATLAB. So let's take a look at a few computer vision issues that we'll talk about a little bit, but just to make you aware of some of the things that people have solved that are very useful in computer vision. So let's take a few moments to look at the following image. I'm going to show it to you, just for a few seconds and then ask you some questions. Okay, so what did you look at first? Who saw pineapples? Did you see bananas? Well, you saw a few things, and it's going to be different for everyone. And so when you looked at the picture, you moved from one object to the next in this image. Some of you might have looked at the papayas. Some saw the pineapples. Some saw the lemons. And what you look at first, second, and third, fourth, and so forth, your eyes are moving around the image from place to place to place, building a picture of what this thing is by looking at the relationship between different locations within patches of image. And so this is a device called an eye tracking system. It has backward-facing cameras, and it measures where your eyes are looking. And with an eye tracking system, like this image, you can literally record where someone's eyes are saccading in order to build representations. And so you start out in the middle here, and you move up, shift around a few local places to look at edges and corners and other edges in the window, and then your eye makes a big shift, and then you're gathering a bunch of information locally, and then you make another big shift, and then you're gathering information locally, and then you make another big shift. And so this big shift followed by local gathering of information followed by big shift is how you construct a representation of what a room looks like, called scene interpretation. This eye tracking device gives you a measurement of the so-called saccade path. And so this eye tracking is also used in retail. Now this is a so-called heat map. And what this heat map does, it tracks your eye movement to show and measure where you saccade, where you look at things. And based on where you look, it records the number of times and the amount of time you spend looking at various parts of the scene. And it colors it from blue being cold or the smallest number of times you've looked someplace, and red being the hottest or the highest number of times you've looked someplace. And so it's called a heat map because it almost looks like parts of it are on fire and parts of it are frozen. But nonetheless, for this heat map, and this is a Best Buy, you'll notice that some areas are regions of the store where people spend more time looking at things. Now, of course, not all things get the eyeballs on them. And so in a retail establishment, they use things like heat maps to understand what is the most valuable part of your retail establishment. And so you're going to put the hot items in those valuable parts because there are more eyeballs looking at it. And if there are more eyeballs looking at it, they're more likely to buy it. And so they use these things to help inform where they place things like the signs, where they place certain types of products. Now, cell phones are immensely useful and immensely lucrative for these retail establishments. And so, look, they place the cell phones front and center in the store, right? That's on purpose. That's a very deliberate decision. You'll notice when you go into a Best Buy, they always place items like the flat screen TVs that are on sale right here as you first come in. That's a deliberate decision because that's where you're going to look first. Okay. So it's also used in package design. And in this particular package design, we have a piece of meat, piece of beef, and you, using an eye tracker, can actually look at where people look first and how much time they spend. And so here we see the first thing people do is they spend a lot of time looking at product. And you'll notice that this window here is quite large. We can have in its glory and splendor a good view of what the product is that you're buying. So then the next place that you look is the tag. You want to look at what is this thing. And then the third place you look is this other part. What is this thing specifically? And what can I do with it? And so when you do package design, you record not only where you look, but also where you habituate, where you spend time lingering, as it were, looking at the product. So it's a deliberate decision that the biggest part of this packaging is this transparent window, so you can see the product because that's where you spend most of your time. And then this label here is off to the right. It's smaller, and then the smallest one is this little tiny thing, relatively, because that's where you spend the third highest amount of time. And so you can use eye trackers for package design. So here's a question. Which one of these is not like the other? So I'm going to flash this quickly. And when I look at it, well, what sort of differences do you see when you look at it? Some are bigger, some are smaller, size, direction. Some are pointing to the left, some are pointing to the right. Okay. Some are different shades of blue. Some are entirely different colors, this red one. And so there are different things that stand out to different people. And you could almost imagine, if you think about it, that the entire thing almost looks like a fish as well. Okay. So when you look at things, the ability to discern visually what or how things are different from one another can become quite important. Another thing that's important in computer vision is looking when things move. And so here at time t0, we have this picture, and we have a stick figure, and imagine at time t equals 1, it's moved. So let's superimpose them and kind of animate that movement. T0, T1, 0, 1, 0, 1. We can make the stick figure dance. But nonetheless, if we put them with one another, an important consideration when you're tracking something over time that's moving is how do you determine where it went from time 0 to time t1. And so that's called the correspondence problem. Where do the pixels in the first version of the image at time 0, what do they correspond to in the next version of the image at time 1? And so in this, you have a naive assumption of having two cameras, and this can be two physical cameras, or can be one camera that moves. And there's a typo. It's naive. Okay. Now, most of the scene points are assumed to be visible in both cameras, and the corresponding image patches should be similar. Don't have to be the same, but they should be similar. Now, what's required is that the distance of the points from the camera has to be much larger than the distance between the cameras. So if the camera moves, it can't have moved to a position that's further away than the distance from the object being imaged to the camera. If you have two different cameras, those cameras have to be closer together than the distance of the thing that you're viewing in the camera. And so your procedure is you have one image, and you search for corresponding patches or regions within this image in the other version of the image from either the second position or the second camera. Now, this can introduce a potentially large search space, and you can use certain constraints to limit the search space, and we'll talk about that. But in order to find this correspondence, where did the pixel or region of image go from time t0 to t1, you need some way to match some similarity measure. And so last semester, we learned correlation. And you can absolutely use correlation over the two patches of image to determine where this patch in the first version of the image went when you took the second version of the image. And so this is an example. You take an image and you move the camera. When you move the camera, in this case, you move the camera to the right. If you move the camera to the right at time t1, the image goes whooshing by in the left direction. So all the pixels move in that direction when you move the camera to the right. So then you take another image. That's your image at time t1. So one question you might want to know, where did this doorway circled in pink go when you went from time t0 to t1? Now, of course, there are a lot of candidates in the image you might search. Maybe it went over here. Maybe it went over there. Maybe it's over here, or maybe it's over there, maybe it's that one. And so you take your original region of image, and then you search within the second image time t1 to see which one of these most closely match or have the highest correlation with this pink scribed region. And so our function then should measure the similarity in the appearance of the pixels in the original. We'll call that a query, F, and each one of these potential targets, we'll call that G. And so why is even correspondence a thing? Why do we care about this? It's used for all sorts of interesting applications. Now, suppose you have two cameras at different poses. You have camera 1 here on the left and camera 2 here on the right. You have an image of some object, the ball, and in the system, well, you know the baseline distance between the optical axis of the cameras. So knowing the distance between the cameras and the angle that this object makes with respect to that baseline distance between the two cameras, knowing this angle, theta 1, and this angle, theta 2, using trigonometry, you can figure out the distance that the ball traces from the camera. And this is called triangulation. You solve using trigonometry for that edge describing the height of this triangle. It's just two right triangles. And so this triangulated distance you can use to calculate the depth or how far away the object is from the cameras. Okay. And so you can use correlation to do this correspondence, and once you have the correspondence, you know it's the same object, and then you can use where that object is to perform triangulation. So if you do this with a camera at multiple positions and these camera images overlap, now you can create a three-dimensional depiction of some object in space by triangulating between every two camera pairs. So you get the distance of this point, this point, this point, and you can construct it in 3 dimensions. And so you might think, well, why should I care about this? Well, this is used in football for 3D instant replay. So let's take a brief look at this. And so their ability to zoom 3 dimensions is because of this correspondence, this photo stitching, and they can fly around and actually create 3-dimensional representations of these players.
I was appreciate the 36 cameras that are stitched all the way around the stadium. We hope to achieve having a replay that you can see from every angle around the stadium to really illuminate how a play happened, why it happened. You're able to play it back and get this basic kind of 360 quarterback, go all the way around. We have to be moving the format. All the information that we capture is being combined between one to the unit file that you can see the.
And these points here are all of the 3D depth points, 3D maps. So now you can create an actual volume outline based on triangulation and it all hinges on this correspondence between pairs of cameras. And this is all happening in real time.
Move around. These plots can come to higher resolution. So when you render the signal, you're actually able to zoom in, zoom out, go a little bit higher, go a little bit lower. It's a really, really cool effect.
Okay. So let's look at this one briefly. It's 3D 360 instant replay. Okay. So let's go forward. Another application of correspondence is so-called optic flow. Now, optic flow takes successive images and it does a correspondence between patches of image from one version to the next and draws a vector describing where that particular patch moved. And how do you figure out where it moved? You do a correspondence. Okay, this is an example of an optic flow field, and the reason why it's useful has to do with the fact that objects that are closer to you move faster. They're in their quote-unquote flow field, and objects that are further away, they don't move by as quickly. And so you can do obstacle detection by looking at your flow field and looking at those regions where you have vectors that have high magnitude. And so in this, you notice that there's something over here that's much bigger than something that's way over here, because the vectors in the center here are a lot larger in magnitude. So this is an example of an optic flow field. And you'll see, as the book gets passed, this flow field is operating real time, optic flow, and you can see as he's passing the book, it's tracking patches of this book. And so that's all I had today. It's just an introduction into how imagery is formed and how it's represented, and hopefully get you motivated by looking at a handful of examples of things that are problems that are solved in computer vision and examples of applications of computer vision that are very, very popular and very interesting. So with that, that's all I had. As usual, please stay healthy, please stay safe, and I'll see you all on Thursday.